You know that feeling when something just doesn't make sense, when your brain refuses to accept what you are being told because it contradicts everything you know about how the world works. That is quantum mechanics for me, for everyone, really. And I mean everyone. Not just you and me, but every single physicist who has ever studied it. Even the people who use it every day, who make calculations with it, who build technologies based on it. They don't understand it either. Not really. And the most remarkable thing is that one of the greatest physicists of the 20th century, Richard Feynman, the man who revolutionized how we think about quantum mechanics, said it out loud. He stood in front of audiences and told them straight up, I think I can safely say that nobody understands quantum mechanics. Nobody. Not him. Not his colleagues. Not the brilliant minds who discovered it. This isn't modesty. This isn't self-deprecation. This is a profound statement about the nature of reality itself. What Feynman meant wasn't that physicists can't do the math. The math works perfectly. I've seen it work. Quantum mechanics is the most precisely tested theory in all of science. It predicts things to an accuracy that is almost absurd. 10 decimal places, 12 decimal places, and every single prediction matches what we observe in experiments. The theory works. It works so well that we've built entire technologies on it. Computers, smartphones, lasers, medical imaging devices, all of modern electronics. None of it would exist without quantum mechanics. So the theory isn't wrong. The calculations aren't broken. What Feynman was saying, what I've come to understand after years of studying this stuff, is that nobody can make sense of what it means. Nobody can picture it in their head in a way that feels right, in a way that matches how we experience the world. The math tells us what happens, but it doesn't tell us why. It doesn't give us a story we can follow, a mechanism we can visualize. And that is what makes quantum mechanics so deeply strange. Think about classical physics for a moment. Newton's laws, gravity, electricity, magnetism, all of that makes intuitive sense once you get used to it. I can picture a ball rolling down a hill. I can imagine the Earth pulling on the moon. I might not have known the equations before I learned them. But once someone explains them, I nod and think, okay, yeah, I get it. The universe is made of objects. They have positions and velocities. Forces push and pull on them. And that determines how they move. It is mechanical. It is like clockwork. Even Einstein's relativity, as weird as it seems at first, eventually clicks into place for me. Space can curve. Time can slow down. Okay, that is strange, but I can sort of picture it. I can build a mental model. Quantum mechanics doesn't give me that. It gives me something fundamentally different, something that refuses to fit into any picture my brain can construct. And I've spent years trying. The problem isn't that we haven't figured out the right interpretation yet. The problem is that reality at the quantum level seems to operate according to rules that are completely alien to everything I know from everyday experience. The rules work, the predictions are perfect, but the rules themselves don't make sense. They're not just counterintuitive. They're beyond intuition entirely. They exist in a space that my brain, that human brains in general, weren't designed to comprehend. Let me give you an example that really drove this home for me. The double-slit experiment. This is the experiment that Feynman called the central mystery of quantum mechanics. It is simple to describe, and it reveals everything that is weird about the quantum world. Here's how it works. You have a source that shoots particles, let's say electrons, one at a time toward a barrier. The barrier has two narrow slits cut into it. Behind the barrier, you have a screen that detects where each electron lands. When I first learned about this, I thought, okay, each electron should go through one slit or the other. You shoot enough electrons, and you should see two bright spots on the screen, one behind each slit. Classical physics says that is exactly what should happen, but that is not what happens. Instead, you see an interference pattern, alternating bright and dark bands, like waves overlapping and canceling each other out. This is exactly what happens when you send waves through two slits. Light waves, water waves, sound waves, they spread out, pass through both slits, and interfere with each other on the other side. But here is the thing that made my brain hurt when I first really understood it. You are sending one electron at a time. Each electron is a single particle. It is not splitting in half. It is not dividing itself between the slits. And yet, somehow, it is interfering with itself. It is acting like a wave that goes through both slits simultaneously, even though it is a particle. And when you detect which slit the electron actually went through, when you measure its path, the interference pattern disappears. Suddenly, the electrons behave like particles again, two bright spots, one behind each slit, just like I expected. The act of measurement changes the outcome, not because you disturb the electron by measuring it, though that is what I thought at first. The change is more fundamental than that. When you don't measure, the electron exists in a superposition, a state where it is genuinely going through both slits at once. Not one or the other, both. And when you measure, the superposition collapses. The electron becomes localized. It commits to a single path. Now my brain wants to ask, okay, but which slit did it really go through? There has to be a real answer, right? Even if I didn't measure it, the electron must have gone through one slit or the other. That is how objects work in my experience. They have definite positions. They follow definite paths. But quantum mechanics says no. The electron didn't go through one slit. It didn't go through the other slit. It went through both. Not in the sense that half of it went one way and half went the other. In the sense that the question itself doesn't have a meaningful answer until you measure. The electron was in a superposition of both possibilities simultaneously, and only the act of measurement forced it to pick one. Feynman spent a lot of time thinking about this, and I've spent a lot of time reading his work. He developed a completely new way of looking at quantum mechanics called the path integral formulation. Instead of trying to figure out which path a particle takes, Feynman said, what if it takes all possible paths at once? Every single trajectory from the starting point to the ending point, no matter how absurd. Paths that loop around, paths that zigzag, paths that go backward in time and then forward again. In Feynman's formulation, the particle explores every possible route simultaneously, and each path contributes to the final result with a certain amplitude. The paths interfere with each other, some adding up, some canceling out, and the result is the pattern you observe. When I first encountered this, I thought it was just a mathematical trick. But it is not. This is how quantum mechanics actually works. The particle doesn't choose a path. It takes all of them, and only when you measure do you get a specific outcome. This is why Feynman said, nobody understands quantum mechanics, and why I completely agree with him now. Because how do I make sense of that? How do I picture a particle taking every possible path simultaneously? I can't. It doesn't fit into any framework. My brain has for understanding motion and objects and cause and effect, and yet the math works. The predictions match reality perfectly. The theory is spectacularly successful. But it refuses to give me a picture I can hold in my mind. The more I dig into quantum mechanics, the weirder it gets. Take superposition. A quantum system doesn't just exist in one state at a time, it exists in all possible states simultaneously until you measure it. An electron doesn't have a definite position until I measure its position. It doesn't have a definite momentum until I measure its momentum. It is not that I don't know these values. It is that they don't exist as definite values until the measurement happens. The electron is spread out in a cloud of probability, a wave function that describes where it might be and how likely each possibility is. And when I measure, the wave function collapses. All the possibilities vanish except one. And that is the outcome I observe. But what counts as a measurement? That is one of the questions that keeps me up at night. Does it require a conscious observer? Does the universe somehow know when someone is looking? That seems absurd to me, but the alternative is almost as strange. If measurement is just interaction with another system, then when does the collapse actually happen? The electron interacts with the detector. The detector interacts with the lab equipment. The lab equipment interacts with the air molecules around it. Where in that chain does the wave function stop being a superposition and become a definite outcome? This is called the measurement problem, and physicists have been arguing about it for a century. There is no consensus. I've read about multiple interpretations of quantum mechanics, each trying to make sense of what is happening, and none of them feel satisfying to me. The most famous interpretation is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s. It says the wave function is just a tool for calculating probabilities. It is not describing something real. Quantum systems don't have definite properties until you measure them. and asking what is really happening before the measurement is a meaningless question. This interpretation works, in the sense that it lets me make predictions, but it doesn't explain anything. It just says, stop asking, do the math, get the answer, move on, and honestly, I hate that. Einstein hated it too. I've always felt a kinship with Einstein's frustration. He spent years arguing with Bohr, trying to find a way to show that quantum mechanics was incomplete, that there had to be some deeper reality underneath. He came up with thought experiments, clever scenarios designed to expose contradictions in the theory. One of the most famous is the EPR paradox, named after Einstein, Podolsky, and Rosen, the three physicists who proposed it in 1935. The idea was to show that quantum mechanics leads to what Einstein called spooky action at a distance. If you have two particles that are entangled, meaning they're described by a single shared wave function, then measuring one particle instantly affects the other, no matter how far apart they are. Einstein thought this proved the theory was incomplete. There must be hidden variables, properties the particles have all along, that determine the outcomes. But experiments eventually showed Einstein was wrong. I wish he'd been right, but he wasn't. Quantum entanglement is real. Measuring one particle does instantaneously affect the other. Not because information is traveling faster than light, but because the two particles don't have separate wave functions. They're part of a single quantum system, and measuring one part collapses the whole thing. This is another thing that makes no sense to my everyday intuition. Two particles can be light years apart, and yet they remain connected in a way that has no classical equivalent. Entanglement isn't like two coins that were flipped together and flew off in opposite directions, each carrying its result with it. It is more like two coins that don't have definite sides until I look at one of them, and the instant I do, the other coin, no matter where it is, immediately commits to the opposite side. Not because a signal traveled between them, because they were never really separate objects to begin with. When I try to visualize this, my brain just refuses. Feynman understood all of this better than almost anyone, and I've learned so much from studying his lectures and papers. He made fundamental contributions to quantum mechanics. He developed quantum electrodynamics, the theory that describes how light and matter interact, and he did it using his path integral formulation. He won the Nobel Prize for this work. He could calculate anything you wanted in quantum mechanics. And yet he still said nobody understands it, because understanding isn't the same as being able to do the math. I can do the math too, at least some of it. Understanding means having a mental picture that feels right, a story that makes sense, and quantum mechanics doesn't give me that. It gives me equations that work, predictions that match experiments, and a reality that refuses to be visualized. There is another principle at the heart of quantum mechanics that makes everything even stranger for me. The Heisenberg uncertainty principle. It says there is a fundamental limit to how precisely I can know certain pairs of properties. Position and momentum are the classic example. The more accurately I know where a particle is, the less accurately I can know how fast it is moving, and vice versa. This isn't because my measuring equipment isn't good enough. It is not a practical limitation. It is a fundamental feature of reality. The universe itself doesn't allow a particle to have both a precise position and a precise momentum at the same time. It is not that I can't measure both. It is that both don't exist simultaneously. This is connected to the wave, like nature of quantum objects, something I've spent a lot of time trying to wrap my head around. A wave that is spread out in space has a definite wavelength, which corresponds to momentum, but it doesn't have a definite position because it is spread out. A wave that is localized to a small region has a definite position, but it is made up of many different wavelengths, so it doesn't have a definite momentum. You can't have both. The universe forces me to choose. And this isn't just true for position and momentum. It is true for energy and time, for angular momentum in different directions, for any pair of properties that don't commute, meaning measuring one affects the other. The uncertainty principle is why atoms have the size they do, why electrons don't just collapse into the nucleus. If I tried to confine an electron to the tiny space of the nucleus, its position would be very well defined, but then its momentum would become incredibly uncertain, which means it would be moving at enormous speeds in unpredictable directions. That motion, that kinetic energy, is what keeps the electron from collapsing. It is not orbiting the nucleus like a planet. It is existing in a probability cloud around it, spread out just enough that the uncertainty principle balances the electrical attraction. This is what gives matter its structure, its stability, not because of forces in the classical sense, but because of the quantum mechanical requirement that position and momentum can't both be precisely defined. So why doesn't any of this make sense to me? Why does quantum mechanics feel so alien? I've thought about this a lot. The answer, I think, is that we evolved to deal with a world of medium-sized objects moving at medium speeds. I didn't need to understand atoms. My ancestors didn't need to understand photons or electrons or quantum superposition. We needed to understand predators and prey and falling objects and moving water. My intuition developed to handle the classical world, the world where things have definite positions and follow definite paths. And in that world, quantum effects are invisible. They're averaged out over trillions of particles. The weirdness cancels itself out. And what emerges is the predictable mechanical behavior I am used to. But at the quantum level, that averaging doesn't happen. I am dealing with individual particles, individual quantum states, and the weirdness is fully exposed. The superposition, the uncertainty, the wave-particle duality, all of it becomes unavoidable. And my brain just wasn't built to handle it. I don't have the cognitive machinery to visualize a particle that is in two places at once. I don't have the mental framework to understand a measurement that changes the past. My intuition fails completely. And here is the thing that I've come to accept. It is not going to get better. I am not suddenly going to discover a new interpretation that makes everything click into place. The reason quantum mechanics feels strange to me isn't because I haven't understood it correctly. It is because it is strange reality. At the quantum level operates according to rules that are fundamentally different from the rules of everyday life. And those rules, those quantum rules, are the real rules. Classical physics is just an approximation, a special case that emerges when you average over huge numbers of particles. The quantum world is the actual world. It is just that I never see it directly. Feynman knew this. He spent his whole life working with quantum mechanics, teaching it, explaining it to students and the public. And he was brutally honest about the limits of human understanding. He said, "I think I can safely say that nobody understands quantum mechanics." He said, "If you think you understand quantum mechanics, you don't understand quantum mechanics," he said. "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical." He knew the theory worked. He knew it was correct. But he also knew it didn't fit into any framework the human mind could really grasp. And I know that now too. That is what makes quantum mechanics so fascinating and so frustrating. For me, it is the most successful theory in all of science. It describes reality with incredible precision. And yet it refuses to be understood in the way I want to understand things. It doesn't give me a story. It doesn't give me a mechanism. It gives me probabilities and superpositions and entanglement and interference, and all of it works, but none of it feels right to me. So what is the takeaway for me after all this time studying quantum mechanics? The takeaway is that the universe is stranger than I ever imagined, that reality at its deepest level doesn't follow the rules I expect, that particles don't have definite properties until I measure them, that objects can be in multiple states simultaneously. That measurement itself plays a fundamental role in determining outcomes. These aren't philosophical speculations, these are experimental facts. I've read about the tests conducted over and over in every way imaginable, and quantum mechanics always comes out right. And maybe that is okay. Maybe I don't need to understand it in the way I understand everyday physics. Maybe it is enough for me to know that the theory works, that I can use it to make predictions and build technologies. Maybe demanding an intuitive picture is asking too much. After all, why should the universe care whether its rules make sense to me? I am just one person, one member of one species on one planet, with a brain shaped by millions of years of evolution in a particular environment. The universe doesn't owe me an explanation I can visualize. But it is still unsettling to me because quantum mechanics isn't just some abstract theory about particles in labs. It is the foundation of everything. Every atom in my body is governed by quantum mechanics. Every chemical reaction, every molecule, every bit of matter and light in the entire universe. All of it follows quantum rules, and I don't understand why those rules are what they are. I don't understand what they mean. I just know they work. Feynman said nobody understands quantum mechanics. And after all my years of studying this, I can tell you he was absolutely right. Not because physicists are stupid, or because the theory is incomplete, but because quantum mechanics describes a reality that is fundamentally beyond the reach of my intuition, beyond human intuition. It is a reality where particles take all paths simultaneously, where properties don't exist until measured, where distant objects remain connected in ways that defy classical explanation. It is a reality that works, that is being tested to extraordinary precision, and that makes absolutely no sense to me, and that, in a way, is the most profound discovery I've made in my journey through 20th century physics. Not just that the quantum world is strange, but that strangeness itself is a fundamental feature of reality. That the universe at its core operates according to principles I can calculate but never truly understand. That is what Feynman discovered. That is what shocked me when I finally grasped it. And that is why, nearly a century after the birth of quantum mechanics, I still don't really understand it. Not me, not you, not even the greatest physicists who ever lived.